Hey y'all. I want to expand a little bit upon just what we know about the diesel cycle. I think I have a little bit of a better grasp of what's going on regarding the diesel cycle now. So I want to just explain some things. First of all, like, what do we know about the diesel cycle, right? We know just sort of the states that are involved in the diesel cycle. So let me just say 1 to 2, 2 to 3, 3 to 4, and because it's a cycle, we have to go all the way back to 1, right? So 1 we know is our isentropic compression. And that just means that there's no change in entropy from like the beginning versus the final state, which the final state in this situation would be the second state, right? 2 to 3 is going to be our constant pressure. Heat addition, right? Sorry, I was trying to teach a video in Spanish earlier. This is the diesel cycle, right? Cool. Now, 3 to 4 is going to be our isentropic expansion, right? Now, I'm going to try and maybe just write some shorthand stuff here just to speed it up. Isentropic expansion, right? 4 to 1 is going to be our constant volume. Heat rejection. Now, we're going to have a few graphs that we end up drawing here, right? You might have like a PV graph or like a TS graph, right? So I'm just going to go ahead and leave those like that. Now, what do we end up having, right? We have first, we're going to have our, actually, no, I shouldn't do that. First, we're going to have our isentropic expansion, which is going to look something like this, okay? It's pretty straightforward. First, let me say that this is a PV diagram. So, yeah. So we're going to have our isentropic expansion, right? So that's going to be, this is going to be maybe our state 1 to state 2, you know what I'm saying? So pretty intuitive, you know? That's what an isentropic expansion looks like. Then we're going to, then we're going to have our constant pressure heat addition, right? I think generally these might be a little bit bigger. So that's our constant pressure heat addition. And we can see that the pressure doesn't change from 2 to 3, right? Cool. Then we end up getting something like this, which is our isentropic expansion, right? Then we have our constant pressure heat rejection. And don't forget your arrows. The arrows are pretty important because those denote what direction the process is occurring in, right? So that's what we have here. And then this is 4. So then you can, if you want I always recommend this. You're gonna draw in what's going on. So the isentropic expansion, that's our compression, we're having work in, right? And if you want to maybe I know this, but let's say I didn't know what to do. I know that really a lot of these things are just opposites. So here I have my work out, but you sort of have to be careful because so I remember in one video I said something like, oh, there's no workout, and I was sort of using a shortcut to produce the method that I needed, right? But or to produce the formula that I needed. But technically there is also workout from 2 to 3. And why is that? So one thing I want you to remember is that we're dealing with a closed system here. So anytime you have expansion, we have this thing called boundary work, right? So there's that expansion of V, right? That V is expanding, right? And so this whole area under is producing that's our work, because work is found by the area under the curve, right? So because that V is expanding, work is being produced. Now, but one thing I want you to see, we also have Q in here, right? Now, that might be a little bit confusing, right? How do we have Q in, and work out? Yeah, I'll get there. And let me just do this. Since it's a closed system, I don't want to sort of throw us off by using dots and everything. And then here, we have Q out. So that's what that ends up looking like, right? Now you might also be able to draw a TV diagram, right? And sorry, TS diagram. And this might be a little bit intuitive as well, right? Isentropic expansion, isentropic compression. Remember, we're dealing with a closed system, right? So your temperature is likely to go up when you're compressing something, and we know that our entropy is not changing, right? So we're just gonna have straight up uh, a line that goes straight up. Let me say, right? Then we have our constant pressure heat addition, right? So let me do this. This is our state 1. This is our state 2, right? So from 2 to 3, we have our constant pressure heat addition, right? What you're going to find is that you're going to have an increase in entropy and temperature. So that's why we get this. And then we have our isentropic expansion, which looks like this. And then it's sort of intuitive, right? When you find things that mirror, right, themselves. This is state 3, this is state 4, and then again, if you want to draw in like your little, we have our work in here. We have our here we have what? We have heat in, right? But we also have work out. So let me just do this, work out. Now I'm just going to do this and then do this, right? So that's work out. And then we also have heat out here, right? Now, how can we maybe I think if you just know these 4 steps, you'll be able to intuitively figure things out. But I want us to look at each state. We can look at each state as its own closed system. And what I mean by that, here's what I'll do. Go ahead and rotate that page. Okay, so now let's look at like states 1 to 2. Okay, now we're always going to start off with this formula because this is literally our GOAT formula. Let me say that in terms of like this whole situation. Now we have Q minus W equals delta U. This Q stands for heat, this W stands for work, and this delta U stands for the change in internal energy. And I want to emphasize that this is Q net, W net, and then that's obviously just the change. Like that's going to be the net change in internal energy. But like, yeah. So, right, from state 1 to state 2, we have our isentropic compression, right? Now, what's that going to look like? We have work going in, right? We can also look at this as, so there are 2 ways to go about it. And I think it might just be easier if you might be able to start taking shortcuts afterward. But like, I want us to just look at it like this for a second. So Q in minus Q out is our formula for work, for Q net, right? Work out minus work in is our formula for work net. So that might be a little bit confusing to you at first, right? So when that work is going out, it's positive, and when that work is going in, it's negative. However, with this method right here, everything is going to be a positive. So like, you know what ends up, like, you know what to put where, I think. That's a good way to say it. So I'm going to leave that as delta U. And the reason I'm putting capitals here is because like, that's just like work instead of specific work or something, right? So for 1 to 2, right, there's no heat, right? It's isentropic, right? Which means it's adiabatic and reversible, right? So we don't have to worry about heat, right? There's no work out, so I can go ahead and cancel that, right? Now, I end up with what? Work in, right? Now my work in is given by, because like I want to point something out. This is a negative and this is a negative, so they cancel out to be a positive, right? My work in is going to be given by delta U. Now what's my formula for delta U? My formula for delta U is actually, I believe it is, well, it's C V delta T, right? And I put that M there just because like we're dealing with like capitals. But if that were a lowercase u, that M would be gone, right? That would be our specific work in, right, in that situation. And I want to just double check myself really quickly. Yeah, I mean, in fact, I don't want to double check myself just to save some time. 2 to 3 is constant pressure heat addition, right? So I'm gonna go ahead and just pick this right up, and I'm just gonna go ahead and say what. So I'm just looking at what I need to like cancel out, right? Now here is sort of the tricky part, right? Okay. So here from 2 to 3, right? We have our Q in, but we don't have Q out, right? We have work out, but we don't have work in, right? So I can go ahead and say that Q in minus W out is equal to delta U, right? Now, a lot of the time, we're going to be solving for work out. You might see something like this: two, work 2 to 3 plus work 3 to 4, right? Is going to be our total workout, right? Something like that. So, like, let's say we're going to solve for our workout. Workout, once you do the whole math and everything, all the algebra and everything, workout is going to be equal to what? Q in minus delta U, right? Now what's that going to look like? Well, delta U we've already said is equal to Q, MCV delta T, right? But let's say, I mean, okay, like that wasn't exactly the smartest. Really, your workout is gonna is a lot of the time it's gonna be PdV, P delta V, right? So we don't even have to worry like P delta V, right? So that is because that's called like our boundary work, like what I said, like that's our expansive work. So that's what that's gonna be. But let's say I wanted to find Q in, right? Let's say that we're asking for the Q in or something, right? Q in is gonna be equal to what? Delta U plus work out. And this is where I feel like this is sort of magical, honestly. So I remember I simplified this down. I know, like just based off of just because I've done this so many times. This is CP delta T, right? But let's say I didn't remember that and I wanted to derive that. Now I know that my formula for U is equal to, you know what, I'm gonna solve this in lowercase just to get rid of our M's and everything. But let's say I wanted to find my Q in. That's gonna be equal to what? U, sorry, that's not supposed to be capitalized. But I'm just gonna leave it as I'm gonna say du, and then that's gonna be minus my work out, right? So yeah, so my du, remember I just said that work is equal to P. Now I'm gonna change these to D's, and I'm gonna say P, I'll make that a capital P, dV, and D really just means like we're integrating, right? It's just bear with me, okay? Now du minus P dV I can also say is equal to du minus PV, and what that looks like, you know what? Let me not let me do this. Okay, actually, you know what? Let's go ahead and say this. I know that PdV is my change in work, right? But let's say I didn't necessarily know, so I wanted to like find my D work, right? So like that's what I'm gonna go ahead and say. We know what the product rule is, right? I will find that this whole term right here simplifies down to this. And you know what? Just to save a little bit of time, go look up my video on, it's called the Legendre transform with enthalpy. And just because I don't want to get into the whole the whole math and everything, just know that this is going to simplify down to this. And you can see what I did in that video. I simplified the steps out and everything. I just to save some time. But basically, I know that U minus PV is the same thing as H. That's an identity. Well, let me not say identity. That's a statement. We call that U minus PV H. Now, what does that mean? I can go ahead and say that I can go ahead and say, what can I go ahead and say? I can go ahead and say this, that Q in is equal to DH. Now what is DH? And now I'm gonna call it delta H, okay? And I'm sort of cheating here, but like it's cool enough in this situation. Now delta H is equal to CP delta T. And I mean, to be honest, I could say that DH is equal to CP dt, and then that we're gonna end up having CP delta T. So what does that mean? One thing I like us to remember Here, this CP is often denoted as constant pressure, right? Now, what do we have here? Constant pressure, right? Now, you might see me in one video say like, okay, like I'm just gonna forget about the work. What is my delta U here? That's not entirely correct. I think I did that just to simplify things a little bit. But this delta U is still delta U. But when we add that PDV, right, or well, subtract it in this situation, right, we end up getting, I'm sorry, we add it. This is supposed to be U plus PV. So U plus PDV. U plus PV is really what is our, this actually simplifies to U plus PV, DU plus PV. Sorry, I sort of got thrown off there. But again, just go and check that whole Legendre equation. You'll see how I simplified that down. But U plus PV is our identity for enthalpy, okay? So, what do we end up getting? That CP delta T is what we can use to calculate our Qin, okay? Now, I want us to look at from 3 to 4. What does 3 to 4 look like? 3 to 4, we have our Q out, right? So, y'all know where I'm getting these numbers from, or these values from. So I'm going to go ahead and say Q out for 3 to 4. There's also work out, if I'm correct. Yes. Is equal to delta U. Now, what might they ask you for? They might ask you for the workout here. Let me see. Workout. It's going to be 1 delta U minus Q out. Yeah, something like that. So, what is that going to look like? Delta U is going to be our C. Let me see. I don't remember this one offhand, so I might have to mess around with it a little bit. CV delta T minus Q out is going to be what? Oh, I'm sorry. There is no Q out, is there? Yeah, there's no Q out. Okay, so Q out is going to be not there. So this is just going to be equal to our CV delta T, right? How does that work? We end up with this, right? So, but like here is sort of the twist. So our workout is normally CV delta T is CV T, the last one minus the first one. But what we might end up finding is that for 3 to 4, you can see that T3 is a higher temperature than T4, right? So the only way for us to end up with a positive is T3 minus T4. And you can see this here, right? This is actually equal to negative delta U, right? Once we divide by -1 or whatever. So that delta U, which is normally equal to T4 minus T3, becomes a negative. So that negative delta U is T3 minus T4. And that's how we get that, okay? And then let's look at 4 to 1. 4 to 1 is what? Q out, strictly, right? There's no work done, blah, blah, blah. So now what do we get? Q out is equal to, let me see, negative Q out is equal to delta U, right? Because there's no work, yeah. Okay, so negative Q out is equal to delta U. Same type of thing, right? So Q out is going to be equal to our negative delta U. That's going to be equal to what? It's going to be equal to CV what? That should be T1 minus T4, right? Is that even possible? No, I'm sorry. So normally, delta U is going to be T1 minus T4, right? And this might sort of be difficult to grasp, but it's the final state minus the initial state. And because we started at 4 here, that's our initial state, ended at 1, that's our final state. So delta U would be T1 minus T4, but negative delta U is going to be T4 minus T1. And I want us to see that that ends up being a positive because our T4 is higher than our T1, right? Cool. So now we can say that T4 minus T1 is our Q out. Okay? So you end up with what? What do we end up with here? Q in there. Okay, let's start from the beginning. So work in is given by MCV delta T. and I'll just say CV delta T for a specific work, right? Q in for 2 to 3 is given by what? That's CP delta T. And I want us to see that that ends up being our constant pressure, right? Here, it's CV delta T, right? And while this might be misleading, like constant volume, yes, because like CV a lot of the time we say is constant volume, but here that's just the way it worked out. We're not doing that because it's constant volume, because as we can see, like this is expanding, right? So we know that our Q in is going to be CP delta T, right? If you wanted to find your work out, simply P delta V, right? So now our work out for 3 to 4 is going to be our CV T3 minus T4, right? And I want to point something out here. Again, this is not because it's constant volume, okay? Like that's just the way it ended up working out. But here we do have constant volume. So what do we end up having? CV T4 minus T1, right? That's that constant volume right there. So now let's say they ask me for the total work out, right? And I'm just going to say specific work out. I'm going to say that that's my V3 minus V2, right? And I can always go back and double check. My V3 is bigger than my V2, right? So that's going to be a positive number, and that's going to be plus what? CV T3 minus T4, right? And what I want you to find is that Q net is so we have a cycle here, right? Our Q net is going to be equal to our work net, okay? So I want to say that my Q net is what? So I mean, okay, like let's say they asked for work net, right? I could say that my work net is equal to my work out, which is this, right, minus my work in. So I'm going to say W out. Now work in is where? Here, right? CV delta T. So I can say minus CV. And what T's were those? 1 to 2. Is my T2 bigger than my T1? Yes. So I'm going to say CV T2 minus T1, right? And this is going to denote my work in. Now, I could also use that to find my work net, which is also equal to my Q net. Now, Q out, I've seen is CV T4 minus T1 written right there above, right? Now, Q net is actually going to be Q in minus Q out, not Q out minus Q in, right? So you have to be a little bit careful for that. So my Q in is going to be what? CP delta T. Let's see, is T3 higher than T2? Yes. So T3 minus T2. And that will denote your work net as well. And that's also maybe if they ask you for Q net. So I think the keys here for the diesel cycle are just make sure you're looking at it as a closed system, okay? It can be tempting because we're dealing with like maybe like, I don't know, like at times like it might be sort of tempting to say like, okay, well like air flows through a car, right? So like this is a closed system, but we're looking at like what's going on in this area specifically. So look at it, you might be tempted to call it an open system, but it's actually a closed system, okay? So I hope this helped. Please don't hesitate to ask comments in the comment section, and please don't forget to like and subscribe, okay? Thanks.